Related rates. An oil rig springs a leak in calm seas, and the oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the patch has a radius of 100 meters? Let's glean information. The area of the patch of oil is A equals pi r squared. We know that because we're told that it's a circular patch. Notice that area and radius are functions of time. The rate of change of the radius with respect to time is dr dt equals 30 meters per hour. We want to find dA dt when the radius is 100 meters. So we're looking for the rate of change of area with respect to time at the moment that the radius is 100 meters. So A equals pi r squared, dr dt, the rate of change of the radius, is 30 meters per hour. We're looking for dA dt, the rate of change of the area, when the radius is 100 meters. The area of the oil patch A and the radius of the oil patch R are both functions of time. I can't emphasize that enough. So taking the derivative means we take the derivative with respect to time. And then what that will do is it will tell us how the rates dA dt and dr dt, how those two rates are related. So take the derivative of both sides with respect to time. Alright, so the derivative of A is dA dt. The derivative of r squared is 2 times r times dr dt. Notice how we're using the chain rule. We are told that the radius changes at a constant rate, so dr dt is always 30. And so dA dt, which is 2 pi r, can be rewritten as 2 pi r times 30. And so dA dt is equal to 60 pi times r. In particular, when r is 100, then dA dt is 6,000 pi, or approximately 18,850 square meters per hour. Let's look at another example. An observer stands 200 meters from the launch site of a hot air balloon. The balloon rises vertically at a constant rate of 4 meters per second. How fast is the angle of elevation of the balloon increasing 30 seconds after launch? Let's draw a sketch of the scenario. Now the observer is 200 meters from the launch site. So that's a fixed value. The height of the balloon is changing, and we're going to call that y, and notice that y is a function of time. The angle of elevation is also changing with time, because of course the balloon is going up. All right, information. The balloon rises vertically at a constant rate of 4 meters per second. That means that dy dt, the rate of change of y with respect to time, is equal to 4 meters per second. We're looking for d theta dt, and that will be in radians per second, when t is 30 seconds. So we want to know how theta and y are related. Well, tangent of theta is equal to y over 200. This is the easiest trig relationship to use. We will use this relationship to see how d theta dt and dy dt are related. So how does the angular elevation, the rate of change of angular elevation, how does that change in relation to how the height changes? So we're going to take the derivative with respect to time. Now the derivative of tangent is secant squared, and then of course use the chain rule, so times d theta dt. The derivative of y is just 1 times dy dt. Now we're going to use the fact that the balloon rises at a rate of 4 meters per second. So dy dt is constant. And that tells us that secant squared is 4 over 200, or 1 over 50. Now we're going to use the identity that secant is equal to 1 over cosine to simplify our equation. Then I'm going to multiply both sides by cosine squared. And so d theta dt is equal to 1 over 50 times cosine squared of theta. All right, I'd like to know what cosine squared theta is at t equals 30 seconds. And that will tell me what d theta dt is. So what's cosine squared theta 30 seconds after the balloon is launched? We're going to find cosine squared theta without actually finding theta. And the way that we do that is we first observe that if the balloon rises at a constant rate of 4 meters per second, then 30 seconds later the balloon has risen 120 meters. And so our triangle will look like this. So at 30 seconds, the balloon is 120 meters high, and the observer has always been 200 meters from the launch site. The length of the hypotenuse is the square root of the sum of the square of the legs. And so the length of the hypotenuse is the square root of 54,400. Now I'm not going to simplify this, and you'll see why. Cosine theta is therefore 200 over that value, and cosine squared is then 25 over 34. So you see that not much would be gained by simplifying that radical, because I'm just going to square it anyway. Using the fact that cosine squared is 25 over 34, we find that at 30 seconds, d theta dt is equal to 1 over 68, which is about 0.015 radians per second, which is slightly less than 1 degree per second. You take care and have a great day.